in Spanish for our friends.
Yeah.
Bueno, buenas noches con todos. El día de hoy nos va a presentar, gracias a su gentil disposición que tiene el profesor Kitazume con nosotros, las experiencias sobre la técnica de soil mixing que aplica por ya muchos años, ¿no? en Japón y que viene trabajando desde los inicios, ¿no? de la técnica ya en Asia. El profesor Kitazume es ingeniero civil con doctorado y es profesor en la Universidad de Tokio, ¿no? Especialista en técnicas de soil mixing, ¿no? Tuve el agrado de conocerlo en el último congreso de Deep Soil Mixing, del cual hemos podido tener este contacto y la disposición para poder compartirnos sus experiencias, ¿no? One more time, Professor Kitazume, welcome for this conference. And I sure that it is the first, but not the end. And the next conference maybe will be in situ, no? Here in Peru. Well,
Yeah.
the auditorium is yours. Okay.
Okay. Thank you very much. Yeah. Okay. Thank you very much for the introductions. Yeah. And then I'm very, very happy to present my, the lectures on the topic of the soil mixing. And then I'm very happy to share them with you. Yeah.
Mhm.
Shall I start my lecture?
Uh, uh,
Or
no, good. Uh,
Yes, you could do it.
sorry?
You could share your screen. That's what.
Okay. Okay.
Yeah.
Just
You are the co-host.
all right. So now and then
no,
I
yeah,
upload my PPT file. Can you see my PPT files?
just,
Okay. Sh shall I start?
but no, not yet, but we can see in presentation mode.
Sorry?
We can see in presentation mode.
Okay. Yeah.
Uh-huh.
But that is it
All
good?
right. Yes.
All
Yes.
right.
Yes.
All right.
Thank you.
You're welcome. So now and then I'd like to start my presentations. Okay, again, and then thank you very much for inviting me to these lectures. So, and then today I'd like to talk about the soil mixing, and then the title is application of the soil mixing method for mitigating the earthquake disasters. So I'd like to show the applications of the soil mixing technology, mainly in Japan. All right. So, and then I think that you can see the several earthquake disasters which were happened in Japan in the recently. So uh, in the most left-hand side, and then you can see the collapse of the buildings which was happened in the Niigata earthquake in 1964. So at that time, and then we encountered such a liquefaction problems. So and then the middle one is the Kobe earthquake. So and then we had a very, very huge earthquake in Kobe in 1995. And then you can see the highway is totally collapsed like that. Recently, 2011, we have another huge earthquake in the Tohoku area. So, and then in this earthquake, we had a very, very huge tsunami attack, and then the tsunami destroyed sort of everything like that. So now and then I'd like to show you our position and then also your positions in the Peru. So and then this graph shows you the epicenter distributions is worldwide. So, and then in the Japan, we located here, this area, and then you in the Peru located these areas. So, and then this graph clearly shows, and then the Peru and then the Japan are located in the circular Pacific seismic belt like that. You can see the red line like that. So, and then your country and then our country have suffered numerous earthquake disasters throughout this history. Maybe you and we are the same, how say, the situations. That according to the internet, and then I summarize the several earthquakes in Peru. I think that you had a very huge earthquake in the 1697, and then at that time, and then the casualty is about 5,000, and then you had a very large tsunami attack. And then also, unfortunately, your country have many houses earthquake. And then recently, that in 2007, so and then you had a huge earthquake, the magnitude of 8 at that time, and then you also have a huge earthquake attack. But in several earthquakes, and then you also had a landslide, maybe the inland area in Peru. So, and then the graph shows the earthquakes in Japan. Also, we have many earthquakes. So, and then these are the very small the list of the earthquake in Japan. So, and then the 1923, we have a huge earthquake in the Kanto, in Tokyo area. The name is a Kanto earthquake. This earthquake had the magnitude of 7.9, and then the number of the dead person is more than 100,000. And then in the 2011, we had a Tohoku earthquake, and then the magnitude is very large of the 9. So, and then the number of the death person is about 22,000. So maybe there are most of them are due to the tsunami attack. This is the one little bit interesting how say the presentations shows, and then this is your country and then our country are connected regarding to the earthquake. So, and then this is the one example, not Peru, but in 1960, and then the Chile earthquake took place. So in the Chile, and then more than 2,000 casualties in the Santiago. At that time, and then the huge earthquake of the 18-meter height attacked Hawaii Island and also Japan. In Japan, and then we had a huge earthquake of the 6-meter height in the attacked Kesenuma is the Tohoku area, and then caused serious damages, including more than 1,000 casualties. So you can see some of the photos. This one is the top is the damages in the Chile, but in the bottom, and then this figure shows the huge damages by the tsunami in Kesenuma Tohoku areas. Right? So now we have to recognize your country and then our country had a very so the potential risk about the earthquake attack disasters. So, and then the earthquake causes many damages, but the one is the factor is a landslide or liquefaction or the tsunamis. So now and then I would like to talk about the liquefactions mainly in these lectures. So as already knows that this graph shows the sort of liquefaction mechanism and the liquefaction chains. So, and then this is the sort of the sequence about the liquefaction take place. At the first stage, and then the earthquake have to take place. And then the shear strength is induced in the ground by the earthquake motions. And then the shear strength enhances the generation of the pore water pressures in the ground. So, and then during the earthquake, and then during the shear strength, induced shear strength, pore water pressure is accumulated, and then the effective stress decreases, and the soil strength decreases. At that time, and then the liquefaction takes place. So this is a sort of the chain to the liquefaction like that. So, and then I would like to talk about the countermeasure of the liquefactions data. So, and then one of the key factor is if we cut this sequence in any place for this place or this one. So, and then we can prevent the liquefactions. So now this graph shows you how much the liquefaction is important factors for the mitigating the earthquake disasters. So, and then this has the figures that listed up is several earthquakes in Japan. For example, and then we have a Niigata earthquake that.
Ya.
Sorry?
¿Cómo? Sí, ya, el viernes regreso muy tarde. Ya.
No,
No, no, no.
it's okay, Professor.
Ya, fíjate, ya. Chao.
I'm gonna put in mute. So, okay.
All right.
Okay.
Okay. Thank you. So, and then again, and then this graph listed up is several earthquakes. All right. So at first, and then I will show you the Niigata earthquake in the 1964, and then the magnitude is 7.8. And then the ground condition is mainly the sand. All right. And at that time, and then the liquefaction took place. So, and then the damages, the amount of damage is mainly the port area, port facility is about the 50,000 million yen. All right. So next, and then I will show another earthquake is the Tokachi Oki earthquake, which was happened in the 1968. The magnitude is 7.9, a little bit larger than the Niigata earthquake. The ground condition is the sand. But fortunately, so and then the liquefaction did not take place in the earthquake. So amount of damage of the port facility is about 2,000 million yen. Okay, so and then the the Niigata earthquake, for example, the yellow one, this one is that liquefaction did not take place. So, and the damage about 160 million. But in the same earthquake, another port area, so and liquefaction took place, and then the damage is about 3,000 millions. All right, and you can see that of the similar the figures. So if you compare with these figures, is green and then the yellows. So it is obvious. So if the liquefaction took place in that amount of the damage is jumped up about, for example, in this case, is about 20 times. All right. So, and then that's why, and then the liquefaction is one of the key factors to, for mitigating the earthquake disaster as much as possible. So therefore, and then in Japan, our the countermeasure technique is focused on the mitigating the liquefaction problems. So, and then now and then I'd like to show you some countermeasures against the liquefaction. So you can see that this is that I can show you the same figures is a liquefaction chains. Earthquake take place, shear strain in the induced, shear strains enhancing the generations of the pore water pressure, and then the pore pressure is accumulated, effective stress decrease and soil strength decreases, and then liquefaction take place. But for example, this is the one that countermeasures, all right, to preventing the, mitigating the shear strains. So, and then one of the countermeasure is the grid type stabilizations. So, in order to prevent enhance the water pressure generation and the soil densification is one of the key, countermeasures. And then the gravel drains is very, very effective for enhancing the dissipations of the pore water pressure, and then unsaturation technique for mitigating the pore water pressure increase. So another technique is increasing the effective stress. Maybe the surcharge the technique is effective to for mitigating the effective stress decreases. And then the cement stabilization technique is very, very effective for increasing the cohesive strength, just the strength of the ground. So, and then this is the key, the countermeasures for preventing the liquefaction. So, and then you don't have to make every countermeasures to prevent. So, and then it is okay if you, if you apply the one of these technique, so and then you can prevent the liquefactions. So and then this graph show you the main list of the countermeasures, liquefaction countermeasures. So for example, is a sand compaction pile method, the Bible rod or Bible flotation, the technique. That is these techniques are categorized in the densification technique. And then the stabilizing is a cement stabilization. In this technique, and then the demixing method or grouting method or quick lime pile method or premix method are included. Okay, so and then there are many the countermeasure of the liquefactions for the liquefaction. So, but today, so I'd like to focus on the cement stabilizations. Okay. There are the many techniques that was developed in Japan and then applied for the preventing the earthquake disaster, or also for increasing the bearing capacity or for the reinforcement. So, and then roughly we can categorize into the two. One is the in situ stabilization, and then the other is the site the stabilization. It is the sort of planned stabilizations. In the in situ stabilization, there are three the technique. One is a shallow mixing method, and second one is the mid-depth mixing, and then third one is the deep mixing method. Which were regarding the depth of the improvement stabilizations. In the case of the exit stabilization, I can list up the two techniques. One is a pre-mixing method, and the other is a SGM, super geomaterial lightweight treated soil method. So, and then I would like to show these technique very briefly, and mainly for the application of the disaster earthquake disaster. Before introducing the application, and then I would like to show you is how say the history of the development of these techniques. So, and then, for example, in the replacement technique, which have been applied for many years, for more than the 1920s, like that. So, and then this technique, this technique was applied to the Kobe Port Island in about 2065. Again, and then the consolidation technique is a vertical drain technique, was developed and then applied in about the 1950s. So, and then this technique have been widely applied to many construction sites. Again, and the compaction technique like that, and then the sand compaction piles was developed is later of the 1950s, right? And then this technique was applied in the Kansai International Airport in 1985, like that. Okay, now and then this is in situ stabilizations. One of the major the technique was a CDM. CDM means the abbreviation of the cement deep mixing technique. And then the technique was developed in the 1960 and then applied to the Yokohama port about the 1975. And then later, and then we developed another deep mixing technique named the DJM, dry jet mixing method. So in this method, we use the powder of the cement in this technique. The CDM is that we use the slurry type the cement like that. So the technique, and then have been applied many the project. One of the project is a Kansai International Airport, and then the other is Haneda Airport constructions. So, and then the plant mixing was later developed in around the 1990s. And then the premix method, SGM method like that. So, and then these techniques are also applied the Kobe or Chiba area like that. Okay. This graph, briefly show you the shallow mixing, mid-deep mixing, and deep mixing about the strength, the target strength, and then the improvement the depth. According to the name, so and then the shallow technique are usually applied to the shallow layer, maybe up to the 5 meters. And then the target strength, of course, it is depend on the purposes, improvement purposes, but roughly speaking, total target strength is around a couple hundred kPa. In the mid mixing technique, is covered in about 4 to 10 meter in the depth, and the target strength is 500 to 1000 kPa. In the deep mixing, right, the target depth is about 5 to 20 or 30 meters, and the target strength is a very variable, but roughly speaking, target strength is 500 to a couple thousand kPa. Okay, and this graph shows the shallow depth mixing. There are many how say the technique. So and then this is the how say, shallow mixing, maybe the horizontal mixing. Okay, I show you these are technique one by one. The one of the has the major one of the shallow mix stabilization is a stabilizer mixing, which has has been applied mainly for the road constructions like that. And then another technique is horizontal and then the vertical mixing. So and then we have a mixing shaft, and then the horizontal, how said, mixing blade are located at the end of this shaft, and then the supply is a cement into the ground and the mix with the original ground by means of the mixing blade. That. Okay. Now and then the mid depth mixing. This has a technique also have a many of the sub techniques. This is the horizontal mixing. It is very similar to the deep mixing, mechanical deep mixing technique. And then you can see the vertical mixing shaft. And then also you can see the horizontal, I'll say the mixing blade at the bottom end of the mixing shaft, like that. This is another type. So, and then you can see the mixing blade on the bottom. At that time, and then this mixing blade rotate is also the vertical, set of planes. In the previous one is a blade is rotated is a horizontal plane, but this one is a rotate the vertical planes. This technique is very unique. We call the trencher type. It's a sort of the chainsaw type. So you can see the chainsaw like that. So and then you can see the mixing blade in several mixing blade. So and then so the chainsaw rotated into the ground, and then we can mix the cement slurry and then the ground by the help of this so the chainsaws. Now and then I would like to show you the dig mixing. This is dig mixing had the roughly speaking is the mechanical one, and then the high pressure injection method is also a jet grout. So in the case of the mechanical technique, and then you can see the mixing shaft, and then there are several, the mixing blade at the bottom end of the mixing shaft, like that. This is the jet grout type. So, and then the high pressures are injected into the ground, and then this jet grout cut the soil, and then mix the cement and then the soils by help of this jet. Okay. Oh no, I show it. I can show. Oh, sorry. So and then I would like to show you the several combination applications. So and then this is the one of the application of the demixing for liquefaction prevention at the Kushiro port is the Hokkaido area. Now and then this is the port facility, right? Sea revetment is the caisson type. This is the original ground. So and then behind the caissons, there are several type of the technique are applied for mitigating the liquefactions. One of the gravel drains, this is the dig mixing, and then this is, this area is not the improved area, but just filled with a gravel. Sorry. And then this is the dig mixing, and then the gravel drain technique are applied there. So, and then fortunately or unfortunately, and then the Tohoku, the Hokkaido Tohoku earthquake was attacked in at the port in 1994, after the grand improvement. So, and then we can see the very clear comparisons for evaluating is the grand improvement. So, and then in the case of the improved areas, you can see that the ground is settled down, and then you can see the very large cracks on the road. But however, in the improved area by the demixing, and then the ground is still flat, and then that there are no damages. So, and then these two figures clearly shows the high efficiency of the ground improvement technique. So now, and then I try to show the grid type deep mixing. This technique was very, common nowadays in Japan. Okay. In the case of the original ground, is that grid. So, and then you can see that this is the ground levels. So, and then when the earthquake attack this the original ground, so and then the soils in this area are induced is the shear stresses like that. So as I explained before, these are shear strains that generate the pore water pressures. So and then after the accumulating to the pore water pressure, and then finally, and then liquefaction will take place. But if we, construct very hard, so the improved ground is sort of the wall here, the grid type. So, and then when the earthquake attack is this ground, of course, and then this ground is not improved area. So, and then they tend to make a shear strength. However, and then this area is reinforced by the very stiff the wall. So, and then the shear strain has remained very small the degree. So, and then we expect very small pore water pressure generated. Mainly negligibly zero pore water pressure generated. So, as I explained before, on the liquefaction chains, so, and then by the mitigating is the pore water pressures, so we can expect to prevent the earthquake liquefaction at this improved ground. Okay, this is a basic mechanism of the grid type. Oh, this is the graph show you the one example of the grid type mixing. You can this is the original ground area, and then you can see is a sort of the grid like that. All right. So and then you can see that this is the curvature like that. So and then we construct is the part of this part of the sort of wall by the demixing, and then we construct the next the columns, and then the connecting is the previous columns very tightly like that. So and then for constructing these columns sequentially to make a large columns for that to construct is a grid types. So we have a very good examples, successful application of the grid types in 1995. So again, and then in 1995, we had a huge earthquake in the Kobe area, in the northern part of the Japan. As I show you this figure before, so and then the highway is totally collapsed like that, and then the part of the bridge falling down, and then the huge buildings is a collapse like that. But I would like to show you the one building here is we call the Oriental hotels, all right, like that. So this hotel was under constructions at the event of the earthquake in 1995, fortunately or unfortunately, okay? So, and then this building, the hotel was constructed very close the shore areas. So, and this is the plain view, sectional view, and then the plain view of the building and then the ground conditions. So you can see the very black line like that. This is the piles, the supporting the main buildings. And also you can see the small, a little bit gray pile like that. So this graph shows this portion shows the grid type improved ground. And this graph shows the plain view. So you can see that it with the large the circles like that. This is the piles for supporting the building. So, and then you can see that these are a grid like that. So this is the grid type deep improved ground by the deep mixing. All right. So, and then under the constructions of this building, so, and then the earthquake attacked this building. So, this figure shows the building and then the surrounding areas. All right. In the surrounding areas, this is the key areas. So, and then there are no ground improvement. So, and then the liquefaction took place. So, and then increasing the very high pore water pressures. These pore water pressures push is the sea revetment to the left-hand side. And then the ground is settled down like that. This figure shows the parking area under the parking area at the building. So, and then this area was already improved by the grid type demixing as shown before. So, and then nothing happens, no damages. So, and then these two figures clearly show the successful application of the grid types. Now, and then I would like to show another earthquake is the 2011 Tohoku earthquake. Again, and then in this earthquake, we had a very huge tsunami attack like that. But in the case of the ground improvement, and then after the earthquake, and then we surveyed is the application of the effectiveness of the ground improvement in several areas like that. So, and then these top figures show the damages in the unimproved ground area, and then maybe the successful applications of the improved ground for the river embankment. And then the middle one is the very similar one for the river embankment and also the road embankment like that. So, and then these figures clearly shows is a successful applications. So, and then this top two, this figure, and then this figures show the block type improvement is that all the ground are improved. Say the improved ground improvement area ratio is say the 100%. But the bottom one is we show the grid type improvement, and then the half of the ground was improved by the grid type. Okay, so in the case of the grid like that, there are no damages also. This graph shows the similar applications of the grid type to the aquamarine buildings, these aquamarines like that. So, and then in the surrounding area, there are no improvement area was heavily damaged. But the main building, which was reinforced by the grid type, so and then the very, very small damages took place. Another application is in the Urayasu city area, Chiba prefecture is very, very close to the Tokyo areas. Okay. Sorry. This is the parking buildings, and then this one. But the top layer here, the area is a liquidable the layers. Okay. So, and then the grid type improvement was applied at this area like that. So, and then you can see is piles for supporting the building, and then these are grid types for mitigating the liquefactions. So, and then this we can recognize is a very nice, successful the application in there. Okay, this is another example, but this the figure already showed before, right? Like that. So now and then the cement stabilizations technique are applied to many purposes. One of the purposes is preventing the earthquake disaster, and of course, and then for the preventing the liquefactions. Okay, of course, and then there are two techniques. One technique is improved the whole area in the ground, as I show you the before. But another type is the sort of grid type, like that. So, and then in this case is the area ratio, improvement area ratio is a 50%. So, and then which is much economical comparing is the whole area improvement. Okay, now and then I'd like to show you another the application is a pre-mix method. Is not the in situ technique, it exists the technique. So this in this technique, and then during the land reclamation, we usually use the sand material for the land reclamation. But the clean sand, especially the clean sand, is easily tend to liquefy so easily. So, and then we put a small amount of the cement with to the sandy materials to enhance is a cohesive strength, not the frictional one, cohesive strength. So, and then you can see that the left-hand side figure shows how say the unstabilized soil sand like that. But the right-hand side you can see is a sand particle and then are little bit covered by the cement. So due to the cement, so and then we put with a small amount of the cohesive strength of this material. According to our researches, 100 kPa in the strength is good enough for preventing the liquefactions. So, and then roughly speaking, in the 50 kilograms to the 100 kilograms per cubic meter is necessary for liquefaction preventions in this technique. Okay. So, and then this graph shows you the one of the application of this technique. Again, and then in 1995, we had a huge attack in the Kobe areas. In the port area, and then the caisson type C revetment is settled and then the falling down because at that time and then the ground behind like that area was not improved. That's why and then the liquefaction took place and then the large the water pressures push is the caissons and then move to the left hand side and then goes down. After the earthquake, and then we excavated this area, and then replaced by the premix technique, as I explained before. This one area is a stabilized soil. Okay. Fortunately, we do not have any huge earthquake after the 1995. So and then we do not have a clear, the evidence for the effectiveness, but we expect this stabilized soil area should be the very nice, show the very good performance for preventing the earthquake liquefactions. So, and then another application is to the Tokyo area. This is the Tokyo Bay area. This is the Tokyo, and then Kanagawa Prefecture on the left, and then the Chiba Prefecture on the right. So, and then the Trans-Tokyo Bay Highway is connecting is the Kanagawa area, and then the Chiba area like that. Underwater, the tunnel like that. Okay. The left-hand side that we call the Ukishima axis. Middle is the Kawasaki man-made island for ventilation. And this is the Kisarazu man-made island in the Chiba area like that. I will show you this area. So, and then premix technique was applied to the Kisarazu man-made island areas. So this is a sectional view, and this was plane views. So, for example, this one is the revetment here, and then you can see is a culvert or the tunnel culvert here. So, and then the premix technique was applied at these portions like that. The main purpose is bearing capacity increase for the load and also the preventing liquefaction preventions like that. So in this case, the design strength is about 400 kPa. And then the cement, the blast furnace slag cement type B was applied. Dosage is 100 kilograms per cubic meters. Like that. So, and then you can see the construction site. So, and then the both ends were covered by the sheet, the pile, steel pile, the circular cell like that. and then the soil, sand to be filled, like this area. So during the filling, we put is this cement for expecting the cohesive soil strength of the 400 kPa. Okay, now I'd like to show you the anticipated the earthquake. Again, and then we had many huge earthquake. Is the Kobe earthquake in the 1995, and then Tohoku the earthquake here is the 2011, like that. So and then unfortunately we had a very huge damages by these earthquake, but we developed the many techniques for mitigating and for minimizing the earthquake disasters. But now and then we have anticipated the very huge earthquake, which covered is the western part of the Japan. The name is Nankai Trough earthquake, this area, that is Tokyo and Osaka, like that. According to the scientists, earthquake scientists, so and then the estimate earthquake and then the damages and the magnitude is about 9, and then which will induce the liquefaction and the tsunami attack. Number of the deaths is about the estimated 300,000. And then the damaged building is about 2.3 million. Economic loss is about 200 billion US dollars. So huge. So for the geotechnical engineers, and then we expected to apply these countermeasures, right, to reduce these damages as much as possible, right? I think that, of course, and then you may have very similar anticipated earthquake motions in the Peru also, and then for you and for the geotechnical engineers will be expected to work for minimizing the earthquake damages. Okay. Now, I would like to move on the concluding remarks. Okay. Now, and then I would like to show the several applications of the soil mix method for earthquake disaster mitigation, especially the liquefaction mitigations. So I show you the several the figures and then the photos. These the applications introduced here clearly reveals that all the methods have the high applicability to earthquake disaster mitigations. So and then soil mixing technique has been applied successfully to various sites, and then the various improvement purposes, and then they are expected to apply for mitigating earthquake disaster in your country, Peru, and then Japan. Thank you very much for your kind attentions. So I hope my the presentations will be helpful for you to preventing and minimizing the earthquake disasters in your areas. Thank you very much for your kind attentions.
Thank you very much, Professor Kitazume. Very interesting presentation that we showed us. I don't know if anybody have questions. I don't know. No sé si alguien tiene alguna consulta para el profesor. Well, I have one in mind, Professor.
Mm-hmm.
You mentioned the importance about control the shear strain in earthquake event.
Yeah.
Is the first way to try to mitigate the liquefaction, no? And in this way, the use to grid type or lattice geometry of deep soil mixing is a way, no, to try to control, no, the strain in the soil. I have that comment because in the maybe first way to understand the liquefaction, more studies try to focus only in the stress share, not to induce the liquefaction. But I think, for example, methodologies to try to control the strain. No, maybe you can have some comments about that for us, please.
Okay. Maybe because just a moment, I how say it goes back. I will go back.
Okay, it's okay.
This one. So and then this as I explained before, and then this is how say the liquefaction, the chains. All right. There are some of the stages: earthquake, shear strain, like that. So and then I have in this in my how say the presentation, and then I how say the show you the several applications, mainly this one. Okay. Of course, and then for example, just one sorry, like that. Of course, and then maybe I'm afraid I might misunderstand your how say the questions. So at that time, please how say tell me again. So and then so in the grid type improvement, we construct is a wall or grid colored gray like that. So and then the important issues in the design is spacing, and also the strength or stiffness of the walls. Of course, and then the spacing of the strength should be designed by the considering is the ground conditions and the expected earthquake motions. All right. So, and then unfortunately, we don't have a detailed design procedures for this uh, uh, technique. Of course, and then some engineers try to make such a detailed designs. But now and then we have said the applied we use is the the how say the ratio of the spacing and then the thickness of the liquidable layers. All right. Of course, and then clearly, if the spacing is become close and close, so and then we expect is a high applicability. But reducing the close and close become the less economical. Yeah.
Okay, I got
Yeah. Yeah.
it. Thank you, Professor. Well, we have some question in the chat.
All right.
We have for Rafael Fernandez. He questioned about it is 20 meters liquefaction limit adequate or can the phenomenon occur at lower depths?
Sorry. Could you say again
Is
about the
that
liquefaction, right? Yeah.
is a 10 meters liquefaction limited adequate or can the phenomenon occur at lower depths?
You mean the 10 meters?
20, I'm sorry, 20.
20. Okay. Yeah. Okay. You mean the how say the maximum depth
Yeah.
for the liquefaction countermeasure,
Uh-huh.
right?
Uh-huh.
Okay. Yeah. Okay. So of course, and then there are how say the several viewpoints. There are several viewpoints. If we have say the focus on the damages of the building, for example, building or the superstructures, all right? So according to our previous the researches, so if the how say the liquefaction take place at a very very deep area, deep portion, deep depths, like for example, so even the liquefaction take place, and then the liquefaction does not affect is the damage cause the superstructures. So as maybe the questioners appointed, so if the 20-meter depth, more than 20 meter, so I think that even the liquefaction take place, this does not cause any damages. So 20 meter is one of the, how say, the uh, criticism. It's a standard to improve the liquefaction. Yeah, to improve the ground, improve the
Mhm.
ground. Yeah, that's right. 20 meters.
Mhm. Okay. Thank you very much, Professor.
Yeah,
We have two questions more, please.
yeah.
Um,
Okay, all right. Don't.
Thank you. For Jorge Umpire, he asked about the stone columns. If is there some limitation about the use respect to the soil? There are some limitation about the use of stone columns?
Maybe may I confirm? You say that stone column,
Uh-huh.
right?
Yeah, stone
Stone
column.
column.
Uh-huh.
Okay, and then stone column, and then okay, sorry, and then I cannot catch up with correctly. Could you how say that explain again?
Yeah, yeah. Is there some limitation about stone columns? It's like a gravel pile
Right.
compactation. Uh-huh.
Hmm.
Is there some limitation about the use in depend of the soil? It is maybe used to in all soils or maybe only in some soils?
Okay, I think that the gravel drains is okay, at least in Japan, and then the stone columns, or the say, okay, I have to clarify the two technique, all right, and then the stone column technique have has has been used for the sandy ground and then the clay ground. And in the case of the sandy ground, and then the main purpose is the liquefaction preventions. And in the case of the clay ground applications, maybe the main purpose is a reinforcement, right, of the
Mhm.
ground, mainly the clay ground.
Mhm.
So I think that so that stone column they usually use the both ground. I think that there are no limitations. I think. And in Japan, uh, we do not stone columns so widely, but we use apply the very similar technique called the sand compaction pile technique. So this technique was applied for the sandy ground to the mitigating the liquefaction and also applied to the clay ground for increasing the bearing capacities. Think that and then that there are no also the limitation. This technique was used clay and the sand depend on the purposes.
Mhm. Okay. Well, we have more question. I am
Yes.
gonna do the last. Maybe the other question I'm gonna text you, Professor, for your time. Well, the last question that we have is about the soil mixing project, no? What is the most common design or execution error you have observed in soil mixing project, and how can it be avoided at the design stage?
So the detailed design for what?
What is the common design or execution error that you have seen in soil mixing project, and how can we avoid that? The principal error.
Design procedures, right?
Or yeah, procedures or design. It's open the question. What is the principal error or most common error that you have been in
Okay,
soil mixing projects?
the design code, you say? Okay. Okay. In the case of the Japan, and then the Japanese government promote these techniques, okay? And then maybe that's the government, several houses, ministries establish their design code and the design procedures, yeah, to the technique. So and then we usually use the one of these code established by the Japanese government. Okay, and then I used to work in the Ministry of the Transport of the government. So and then I established one of the design code for the cement stabilization. Fortunately, and then the design code is still working. Yeah, for the designs. All right. Of course, and then I don't know that in the your situation in the Peru, yeah, of course, and then for example, the government or the society will establish the code. I think that you can how say that use as the Japanese code, or I think in US federal highways establish another code. So and then you can refer these code to establish your design code, I think.
All right. Yeah, we are we start first of all to have a commit about soil improvement commitment right now, and yes, this there is a way, to try to establish a code, to do standard designs, to have a very quality about criteria about the design. Well, thank you very much, Profesor Kitazume. Maybe si tienen más consultas, pueden escribir al interno al chat o al link. Acá al chat yo mando un correo para el profesor. ¿Sí? Bueno, thank you very much, Professor Kitazume, for your time. Maybe we are going to see you in another opportunity. Thank you very much.
Thank you. Yeah, hopefully. Thank you very much again. Yeah, I also show my how to say sincerely the thanks to all of you. Thank you very much. Yeah.
Thank you very much.
Bye-bye. Bye-bye.
Bye-bye.
Bye-bye. Good night.
Valeu.
Bien. Igual gracias a todos por participar, todos los presentes. Nos vemos en una próxima oportunidad.
Gracias, Walter. Perdón, Álvaro. Chao, gracias.